Hi guys! So we are picking up with, we ended at the Ferris wheel problem yesterday. I want to continue on and move on with the non-uniform circular motion part. So this is beginning section 6.2, and our goal is to get completely through section 6.2 in this video. So then that way we can focus on 6.3, 6.4. We may also get all the way through 6.3. I'm not sure. We'll see how this goes. In terms of non-uniform circular motion, so we've talked about if it's not uniform circular motion, then I'm going to have two components for that total acceleration vector. So remember, we'll have some type of radial acceleration, and we're also going to have a tangential acceleration. So that same thinking that we talked about in chapter 4 is also going to be similar thinking in terms of forces. So just like the acceleration has components in terms of total acceleration, force will also have components. We're going to call Fr the force that's going to be producing the centripetal acceleration, so we can think about that as like the radial force, which should make sense because my acceleration in my radial acceleration is still that mv squared over r. And then my tangential force is what's going to produce that tangential acceleration. So still same thing in terms of components when we thought about it in chapter 4 with acceleration. It's just now we're thinking about it also in terms of forces. So we could say the total force then would be my radial force as well as then my addition of that tangential force. That would be the sum of the forces, that net force. Okay, so let's look at an example here. If we're thinking about a vertical circle with non-uniform speed, it says a small sphere of mass m is attached to the end of a cord of length r. So I have a small sphere here, it's attached to this cord, and that cord has a length r. And it's set into motion in this vertical circle about some origin point. So there's my origin. Determine the tangential acceleration of the sphere. So that's the first part that I want to do, so let's just answer that question first. Then we'll answer the next one after we get this first one. So I want to determine the tangential acceleration. So I need to think about this then in terms of this tangential acceleration. I know I'm going to have it when I'm moving at some kind of angle here, right? So I want to find, let's look at this piece of the puzzle. Let's look at when the mass is right here at this point on the circle. So when it's right here, I know the forces that are acting on that mass are weight force, and then there's also tension. So I'm going to have my weight force going straight down. Tension is at an angle here, so let's draw this. So I have my weight force, and then tension was at an angle. Okay, well, I'm going to break up weight into components. So here's theta. This would be mg cosine theta, and that would be mg sine theta. Okay, if I'm thinking about this acceleration, I know that the tangential acceleration is going to be which one of my forces. So if I'm thinking about the tangential acceleration, I'm trying to think about where that tangential acceleration would be at on this picture. So if we're right here, we know that tangential acceleration is going to be tangent then to that mass. So if I'm looking at my picture here, it's going to be my mg sine theta. So if we go back to our free body diagram, this is going to be causing that tangential acceleration. So tangential force is going to be mg sine theta, and that's going to equal, because we know that it's moving, it's accelerating, is going to be equal to mass times acceleration. Specifically, that acceleration is my tangential acceleration. And I'm trying to find an equation that will show me what my tangential acceleration will be. So I want to rearrange all of this. If I have wanting A, if I divide both sides by m, the m's cancel out, so then I would have my tangential acceleration just equals g sine theta. Okay, so this would be my answer for that tangential acceleration. And I chose that this would be that tangential force because that would be the one that would be moving tangent to that circle. So this would be the force producing the tangential acceleration. So we can set those two equal, masses end up canceling, I get g sine theta. Well, let's look at the second part of that problem. The second part of that problem says, determine the tension in the cord at any instant when the speed of the sphere is v, and that when the cord makes an angle with the vertical. So I want to find tension, in the cord at any instant when speed is v and the cord makes an angle. So I need tension in terms of v, and also thinking about it in terms of theta, of an angle. So let's go back to our free body diagram. On our free body diagram, if I'm thinking about, this would be radial forces, right? Because tension is acting along the radius. So I want to think about the sum of the forces that are in the y direction, because that would be what's giving me my radial force. So my sum of the forces for the radial forces, or this would be in the y direction because my circle is moving this way, the tension is moving along then that radius. So in this case I would have, and we know the radial, my radial acceleration will be caused by those two forces there. So my radial forces are going to be tension. So I have tension, and then it would be minus mg cosine theta. And since tension is what's causing that centripetal force, it's causing that centripetal acceleration, we know that that's equal then to mv squared over r, because it's the centripetal acceleration. So that means I'm going to have the v squared over r as that radial acceleration. So now they want us to just rearrange this so that way we can have something that would be set equal for t. So my tension would be equal to mv squared over r plus mg cosine theta. And oftentimes when we find the tension, they're going to want you to compare it to a factor of mg. So if we do that, we can write this equation, but let's factor out mg so then that way we can see what that looks like as well. If I do that, I would get t equals, I have mg. So if I'm factoring out mg here, I'm going to get v squared over rg, and then plus cosine theta. So that would be my formula, or my equation or expression to represent tension. So that would be answering our question, that second question, of determine the tension in the cord at any instant. So I knew we explained that in terms of v and in terms of theta. So we answered that question. Okay, starting off with the motion and accelerated frames, we kind of touched on just a little bit that there are such things as fictitious forces, and a fictitious force results from an accelerated frame of reference. So that means they're coming from non-inertial reference frames. The fictitious force is typically due to observations that are made in an accelerated frame. They appear to act on an object just in the same way as a real force would act. But the problem is that we can't identify the second object that the fictitious force is acting with. So that's how we know it's a fictitious force. We said that centrifugal force is a fictitious force. There's actually no such force as that. We think that there's one because we feel like when we're negotiating our curve in our car, our body feels like it's moving outward. So you're feeling like an outward pull. But it's really just because as you're taking that curve, your body still has inertia, still wanting to move in that straight line, which is why your butt kind of moves a little bit up off of the seat. So real forces are always going to show us an interaction between two objects. That's super important. It's really going back to Newton's third law, where they're saying that for every action there is an equal but opposite reaction. So I have to have some type of interaction between forces to have a real force there present. A fictitious force is really only acting on one object, and we don't really see an interaction between things. So simple fictitious forces appear to act in the direction opposite that of the acceleration in a non-inertial reference frame. So the centrifugal force is a good example of this. Guys, I'm going to stop here because the bell has rung and it's beginning 7th bell. We are going to do some more practice problems, more whiteboard problems tomorrow, doing things like this with non-uniform speed and in terms of forces and acceleration. So we will also probably pick up with the rest of this tomorrow if we have time for the whiteboard problems. If not, you'll have another video tomorrow. I will see you tomorrow. Have a great night. Bye.